We are now starting with Lecture 13, and we're going to continue with the problem of equilibrium, the problem type given K, and the initial concentrations determine other concentrations. So here is another example problem. Under certain conditions, nitrogen and oxygen react to form dinitrogen oxide, N2O. Suppose that a mixture of 0.482 moles of nitrogen and 0.933 moles of oxygen is placed in a reaction vessel of volume 10 liters and allowed to form N2O at a temperature for which the equilibrium constant in units of molar is equal to 2 times 10 to the minus 37. What will the composition of the equilibrium mixture be? So, of course, the first thing we need to do is start with a balanced reaction so that we know the stoichiometry. And now we will fill out our reaction table. Since we are given Kc, which is in units of molar, and I have moles and liters of material, it makes sense to do my reaction table in units of molar. So when I fill out my initial, you notice that I take 0.482 and divide by 10 in order to get 0.0482. And I do the same with oxygen, and initially we have no product. The reaction is going to move forward. So you notice that I have 2 nitrogens in my balanced reaction, so I have to have minus 2x on my delta row for nitrogen, minus x for oxygen, and plus 2x for my N2O. Now I bring my values down to the equilibrium row. Of course, Kc is products divided by reactants raised to the coefficient. Everything is in gas form, so my Kc representation is right here. And now it's just a matter of substituting in my representations on my equilibrium row to equal 2 times 10 to the minus 37. So now we can continue with the math. Now at this point, the math could get very complicated. In fact, you can see that we will wind up with an x cubed term. But maybe there's something we can do to simplify our math and make this easier to solve. I notice Kc is a very, very small value. So that means that not much N2 or O2 are going to react and drain away our initial concentrations. So when I look at the reaction table, it is reasonable to assume that 0.0482 minus 2x is probably pretty close to 0.0482. And 0.0933 minus x is probably pretty close to 0.0933. This makes my math a lot easier. So now, when I go back to my solution for the concentrations, if I get rid of those x's in the bottom and set it equal to Kc, it becomes a much easier mathematical problem to solve. Of course, I'm going to cross multiply and get 4x squared equal all these terms multiplied together. And eventually I'll have to divide by 4 and take the square root, and I wind up with x equal to 3.3 times 10 to the minus 21st molar. So now let's go back and look at our reaction table, knowing our approximate solution of x, and see if that's close enough. So if I look at 0.0482 minus 2 times this value right here, which is very, very tiny, it's still 0.0482. And the same thing with the oxygen concentration. So my assumption that x was negligible compared to the initial concentration is good. As far as the N2O is concerned, things are significant relative to 0, so I notice that I have represented this concentration as 2x, so that means it's 6.6 times 10 to the minus 21st molar. And now I've solved this problem. So how good was our assumption? Pretty darn good. So the learning here is if you have a very, very small equilibrium constant, often you can ignore the x terms relative to the initial concentration. And if you ever wonder if that's correct, you can always check your assumption, and if the value of the initial concentration is still equal to the value of the equilibrium concentration when you subtract that x value, you know your assumption was good. Here's another example. The reaction between CO2 and H2 yields carbon monoxide and water vapor, and we're given a Kp value of 0.64 at the temperature we're doing this, which is 900 degrees Celsius. For reactant partial pressures initially at 1 atmosphere, what are the equilibrium partial pressures of all the gases? So once again, it's very important to start out with a balanced reaction. And this time, we notice that all our coefficients are equal to 1. We are given Kp, which means we need to work in units of atmospheres, so that's perfect. The Kp value is going to be the pressure of the products over the pressure of the reactants. And when I fill in my table, initially carbon dioxide and hydrogen are at 1 atmosphere, and my products are at 0 atmosphere. The reaction is going to inch forward a bit, and now I have my equilibrium representations for the pressures. So with my Kp expression, I substitute my x values, and I have this expression here. Now again, we can think about doing something to make our math simpler, because if we multiply this out, we're going to get x squared terms. But maybe you notice there's something very easy we can do to simplify the math. We can represent our expression as x squared over 1 minus x quantity squared equal 0.64. And I could take the square root of both sides. That would get rid of my x squared and only give me x. So again, I have much simplified math. And when I make my solution, x is going to be equal to 0.44 atmospheres, and my product concentrations are going to be 1 minus x, or 0.56 atmospheres. So when you're doing these problems, look for ways that you can simplify the math. Now, a few words about units in the reaction table. I've given you 2 examples. In the first, molarity was used, and in the second, partial pressure was used in the reaction tables. And I did that so that my reaction table units agreed with the units of my equilibrium constant. You may also remember that when we first started with reaction tables, we used moles or millimoles. All these are fine, but you need to be consistent and careful with your units. I remind you that molarity is moles divided by volume. So in this simplified example, if you had A going to 2B and initially started out with 0.5 molar, you notice that if we were to go forward this tiny amount of 0.075 molar, you would of course match the reaction stoichiometry and have plus 0.15 molar here, and your equilibrium concentrations would be in units of molar. But if, for example, you had the same problem and you were told that you have 5 moles of material in 10 liters, your reaction table would be similar, except off by a factor of 10. And if you were working that problem with your reaction table in moles, you would have to remember to divide the values by the volume before setting it equal to Kc, because Kc is in units of molar. And as long as you remember to do that, it doesn't matter if you divide by the volume first and work your table in molarity, or divide by the volume second and work your table in moles. Either way, you should get the same answer. The same theory works when we are working with partial pressure, which is proportional to the number of moles of gas. I'm sure you remember that PV equal nRT, which means that the pressure of a gas is directly proportional to the moles of the gas times RT divided by V. So, back to my simplistic example. If you are given your initial concentration in units of pressure of, say, 1 atmosphere, you would work your delta rho and your equilibrium rho also in units of atmosphere, keeping in mind the stoichiometry is 1 to 2. But if you were given the problem where you had moles of gas, and instead it was 4.10 moles of gas, and the gas was in 100 liters at 298 K, you can work your reaction table in moles, but you're going to need to convert it to pressure in atmospheres before plugging it into the Kp expression. So in the example on the left, if you're given pressure and work your table in pressure, you can substitute directly, and you will have this Kp value of 0.0105. If you are given moles, keep in mind that you're going to have to take these moles and multiply them by RT over V, which is the correction factor to go from moles to pressure. And as long as you do that consistently, once again, you have equivalent answers. The bottom line is, if you're working in Kc, make sure by the time you set it equal to your Kc value, it's in molar. If you're working in Kp, make sure before you set your expression equal to Kp, your values are in units of atmospheres. Of course, if you ever luck out where you have a reaction where the change in moles of gas is 0, your moles will be directly proportional to your atmospheres, so you won't have to do any conversion. So here's an example of working a reaction table with Kc, and we have a reaction at equilibrium in a 500 ml flask contains 0.025 moles of H2, 0.025 moles of F2, and 0.268 moles of HF. What are the new equilibrium concentrations if 0.200 moles of HF are removed and we're given the Kc value? So you notice we always start with a balanced reaction. It's important to know that there are 2 moles of HF in this reaction. So now we can set up our table. And let's say that you decide you are going to do your table in units of moles. So I'm going to directly put 0.025 moles of H2, 0.025 moles of F2, and my initial concentration was 0.268, but I perturbed the equilibrium by removing 0.200. So now my concentration is 0.068 moles. Now, of course, when you remove some product, you are going to shift the equilibrium to the right. So it's going to unge forward at -x, -x, and plus 2x. Our x here is in units of moles, and here is our representation of our equilibrium concentrations. Of course, before we substitute this in our equilibrium expression, we are working with Kc, so we need to work in units of molar. So you notice I am now dividing by the number of liters, which is 0.5. Kc is, of course, products divided by reactants. So now I have my expressions. And since H2 and F2 are the exact same expression, I just have 0.025 minus x divided by the volume squared. And hopefully you notice a few things you can do to simplify this. Number one, we're in a lucky enough situation that the change in moles of material is 0. We have 2 molar going in, we have 2 molar going out, so our volumes are going to cancel. Hopefully you notice another thing you can do from a previous problem to make this easier, and that is to take the square root of both sides. So doing that gives me this expression here, which is much easier to solve than something with x squared. Now, of course, I cross multiply. So I have this on top and these two multiplied to give me this expression. I am going to solve it and group my x's together. And by the time I'm finished, x is equal to 0.0157 moles. So if I go back to my reaction and substitute that 0.0157 to get my final molar amounts, and of course, if you're asked the concentration in units of molar, not moles, we can divide by the volume, and these are my final concentrations of H2, F2, and HF. And if you'd like to check the answer, you can always substitute your final concentrations into your equilibrium expression, and as you can see, it does turn out to be equal to the value we were given for Kc. So here is my question for you. Determine the concentration of ClF3, ClF, and F2 from the decomposition of 5.32 molar ClF3, and I've given you the Kc value and the balanced reaction. Everything is in the gas phase. We are given Kc and the initial concentration of 5.32 molar. We're in the correct units for the equilibrium constant that we have been given. So we're going to start out with an initial row, and we have 5.32, 0, and 0. On our delta row, the reaction is going to go forward. Everything has a coefficient of 1, so it's minus x, and plus x. So at equilibrium, this is our representation with x of what the concentration should be. Our equilibrium expression is products divided by reactants, which is, of course, x times x over 5.32 minus x, set equal to our Kc value of 2.76 molar. So when we cross multiply, we have x squared is equal to 2.76 times the quantity 5.32 minus x. So that, of course, gives us x squared equal 14.68 minus 2.76 times x. This is going to turn into a quadratic that we need to solve. Because the Kc value is somewhat significant, we cannot assume that x is tiny compared to 5.32. So we are going to have to solve a quadratic. So of course I will bring everything to one side and set it equal to 0. So now I have this expression here, which you can solve using the quadratic equation. I remind you that the coefficient in front of x squared is a, the coefficient in front of x is b, and the coefficient in front of x to the 0 power, or nothing, is c. So I show you the solution to the quadratic equation, x equal negative b plus or minus b squared minus 4ac, square root of that quantity, the entire quantity divided by 2a. And of course, you're going to substitute 2.76 for b, 1 for a, and minus 14.68 for c. You'll wind up with two answers. One of them will be negative, which doesn't make sense since the reaction is going to go forward. So use the answer in which x is equal to a positive value. And once you resubstitute that into your table, you can solve for the materials. Our ClF3 will be 5.32 minus x. Our ClF and F2 will equal x. So I hope that helps you solve this problem.